Good evening, good morning, whatever time of day you're watching this podcast. We are going to start learning about confidence intervals. And if you were in class last Friday, we did an intro activity using Valentine candy hearts. And each person in the class got a sample of about 50 hearts. And we used that statistic, the proportion of pink hearts in your sample, to create a confidence interval. And so we're going to take some formal notes on confidence intervals today. So as we head into statistical inference, that's basically using sample data to estimate parameters. We're going to be focusing on confidence intervals, which in your book is sections 8.1 and 8.2. Okay, once we get through confidence intervals, then we'll go on to hypothesis tests. So we're going to be going out of order in the book a little bit in these next few sections. So statistical inference, everything we do in statistical inference is going to be based on what we learned about sampling distributions. So if we were to take multiple samples over and over and over again, what would the sampling distribution look like? And so when we do confidence intervals, we use that same kind of theory. What would happen if we use the inference model many times? When we do statistical inference, it's important that our data is random and that the design is random. If it's not, then your conclusions may not be valid or as accurate. So it's real important for you to have random data. Okay, confidence intervals can be constructed for means or proportions, and everything we're going to be doing in the next unit, we're going to be focusing on proportions, and then we will come back to means. And what a confidence interval does is it gives you an interval of possible values for whatever characteristic you're trying to estimate, which is going to be a population proportion. And when we construct a confidence interval, we choose a degree of confidence. So in class on Friday with the Candy Valentines, we did a 95% confidence interval. You can really choose whatever confidence level you want. Common ones are 90%, 95%, and 99%. Okay. And once you choose your level of confidence, then you should have good reason to believe that the population parameter will lie between the two values in your confidence interval, the lower and the upper bound. Okay. When you construct a confidence interval, when you interpret your level of confidence, and we talked about this on Friday, so those of you who weren't here, you're going to really want to talk with somebody in the class or get with me, and I'll probably go over this the next time we have class. But again, it's that interpretation of 95% confidence means if we were to construct intervals over and over and over again, 95% of the intervals would contain the population mean. And that's kind of what we saw in class on Friday. With such small class sizes, you know, we probably only had about 20 intervals, but 19 out of the 20 would capture the true parameter, the true proportion of pink hearts in the big bowl. If we did 100 intervals and we did a 95% confidence interval, then 95 out of the 100 would capture the true parameter, which then means 5% would not contain the parameter. Okay, as I mentioned earlier, everything we're going to be doing in the next few units is with proportions, and it's going to tie back into everything that we learned back in Chapter 7 about the sampling distribution for a proportion. So please remember that the difference between P and P hat. P is the parameter, P hat is the statistic, which means it comes from a sample. And then we learned these three characteristics about the sampling distribution for a proportion. The center of the sampling distribution of all the P hats will center at the true proportion. To get the standard deviation of the sampling distribution, we use the following formula. To check for normality, we check that n times p and n times 1 minus p are both greater than or equal to 10. And then it's also important to check for independence and that the population is at least 10 times the sample size when we're sampling without replacement. So all of those concepts that we learned in the last chapter are going to carry forward into these next few sections. Okay. Confidence levels. When you choose your confidence level, you're basically picking the success rate of the method that you're using to construct the interval. 90, 95%, and 99% are the most common, but really you could have an 84% confidence interval if you really wanted to. But as I mentioned, these are the most common confidence levels. Once you choose the level or are given the level, you have to determine the corresponding z-score, which really from here on out we're going to start calling the critical value or z-star. Okay, so you're going to get this from your calculator or table A. Okay, and that's what we're going to focus on these next two slides, is how to get the correct critical value based on the confidence level that you choose for the confidence interval that you're constructing. Okay, so first we're going to talk about finding the critical value or z-star for a 95% confidence interval. So if you remember from Friday, this is the formula we used, and this should look familiar. Statistic plus or minus, z-star is your critical value, and then the square root is the standard deviation. So it's statistic plus or minus your critical value times the standard deviation of the statistic. And on Friday, we did a 95% confidence interval, and we know from the 68, 95, 99.7 rule that when we're dealing with a normal distribution or a distribution that's approximately normal, 95% of the data will fall within 2 standard deviations. So in class on Friday, we used a critical value of 2 because 95% of the data will fall within 2 standard deviations. That's not remember the 68, 95, 99.7 rule is an approximation. The exact critical value for a 95% confidence interval is 1.96, which is very close to 2. But let me show you how you actually get the 1.96 using Table A or using your calculator. Okay. So what we want to do if we want to find the z-star for a 95% confidence interval, if we think of our normal curve, we want the p-hat values that are going to fall within that middle 95%, okay, within that middle 2 standard deviations. So if the area under the curve that I've highlighted and represented by the 95%, that leaves us 5% for the 2 tails. So if I take 0.05 and divide it by 2, that gives me 0.025 in each tail. So 0.025 in the left tail and 0.025 in the right tail for a total area under the curve of 1. So your critical values can either be found here or here. It doesn't really matter either way. But when you use Table A and you have the area under the curve, remember the table always gives you the area to the left. So using Table A, if you look in the middle of the table for 0.025 or for 0.975, okay? So this area right here is 0.025. Okay, but the area from here all the way over to the left would be 0.975. So if you look up 0.025, you're going to get a z-star or z value of negative 0.128. And because of the symmetry of the curve, if you look up 0.975, you're going to get positive. I'm sorry, not 1.28. You're going to get negative 1.96. Let's try this again. Or if you look up 0.975, you're going to get positive 1.96. I was jumping ahead of myself. Sorry about that, ladies. If you use the inverse norm command, okay, you have to give the area to the left, so you would do 0.025, or you could put in 0.975. And remember, to get inverse norm, you go to second vars or to the distribution menu, and this will give you negative 1.96 and positive 1.96. And you're always going to use a positive value for z-star. So for a 95% confidence interval, your critical value to compute the interval would be 1.96. Okay? So let's try one more, and we should be able to go a little bit faster. So if I want to find the critical value for an 80% confidence interval, okay? Not a common confidence level, but that's okay. I want you to be able to find the z-star. So again, picture your normal curve, and if you want an 80% confidence interval, that means you want the p-hats that fall within that middle 80% under the approximate normal curve. So that leaves us 20% for the tails. So if we divide it by 2, that's going to give us 10% in the left tail and 10% in the right tail. So if I want to find this z-star, okay, you're going to look up either 0.1 or 0.9 in the middle of table A and find the corresponding z-score. Or you can do inverse norm on your calculator for 0.1, or you could use 0.9. And again, this z value here is going to be negative, and this one on the right will be positive. So if we do inverse norm, you'll get negative 1.28 if you do positive 0.1. If you do 0.9, you'll get positive 1.28. And that's what you should get if you're using table A, either in the back of your book or in your goldenrod formula sheet. So the critical value for an 80% confidence interval would be 1.28. Okay? Let's try one. So find the critical value for an 88% confidence interval. So again, you're going to draw your normal curve. You want the p-hats that are going to fall within that middle 88%. So that means we have 12% left for the two tails. So if I divide that by 2, I get 0.06. So 0.06 here and 0.06 there. So for this z-star, I would do inverse norm 0.06. So if I do second distribution, inverse norm, and I do 0.06, I get negative 1.55. And then obviously for this z-star, and I don't have to do it because we know the normal curve is symmetric, and I should get positive 1.55. But if I use that inverse norm command, I'm going to put in 0.94 because that's the area to the left. So if I do inverse norm for 0.94, I do in fact get positive 1.55. So the critical value would be 1.55. Okay? So that's how you're going to find your critical value. All right. These are the common confidence levels, as I said before, 90%, 95%, 99%. Here's the corresponding tail area. So the left and the right tail will have 0.05 in each tail for 90%. And then here are the corresponding z-scores. So again, 1.96 is really close to 2 standard deviations, but the 1.96 is just more precise. You'll probably get used to these 3 z-scores because, like I said, 90, 95%, and 99% are the common confidence levels. But I don't want you to memorize them, but in time, you'll probably just become familiar with them. Here is the generic formula for a confidence interval for a proportion. So p hat, you can just think of it as statistic, plus or minus your critical value times the standard deviation. Okay? And sometimes this is called the standard error when we're talking about a sampling distribution. Okay? The other thing I want to point out is I know that back in Chapter 7, the formula for standard deviation was the square root of p times 1 minus p over n. Notice we are using p hat because we don't know what p is. We don't know the population parameter. The whole reason we're doing this is to estimate it. So our best estimate of p at this point in time is p hat. So when we go to calculate the standard deviation, we are going to use p hat instead of p. Okay? So this is the generic formula. This part of the formula right here is called the margin of error. And we will talk about that a little bit more when I see you next. So what comes after the plus or minus in the formula for a confidence interval is the margin of error. And you may have heard that in different political polls. A lot of times they'll estimate a parameter with a statistic, and they will quote or give a specific margin of error. So just kind of be on the lookout for that. Okay, we're almost finished here. There's 3 conditions you need to check before you construct a confidence interval, and they are, first and foremost, that your data comes from a simple random sample, and this kind of gets overlooked a lot of times. It's not going to do you any good if your sample doesn't come from the population of interest. Okay. Second condition is to check for normality because we can't use z-scores or find a critical value if the sampling distribution isn't normally distributed. And so these should look familiar. We did these back in Chapter 7. Again, we don't know the true value of the parameter, but at this point in time, our best estimate is the statistic that we have collected. So it's going to be n times p hat and n times 1 minus p hat. And if both of those are greater than or equal to 10, we can assume normality, which allows us to use z-scores. And then the third one is the population is at least 10 times the sample size, and that allows us to check for independence when we are sampling without replacement. Okay? So those should look familiar to you. Not least, we talked about this in our little activity on Friday. At the end, once you've constructed your confidence interval, you are going to interpret it using 2 sentences. We are blank % confident, so normally that's either 90, 95, 99% confident that the context of the problem, proportion of pink hearts in the big green bowl, is between lower value and upper value, 10% and 22%. Okay? The plus or minus in the formula will, obviously the minus will give you the lower bound and the plus will give you the upper bound. And then the second sentence is very, very important, and that's where you talk about that how you understand what the meaning of the word confident. And this is, again, if you were to do this over and over again, if you were to construct 100 intervals, then 95 out of the 100 should capture the true parameter. So that's what you mean by 95% confident. So by 90% confident, we know that 95% of all possible intervals, so again, if you were to do this over and over and over again, 95% of them will capture the true parameter. Okay. In your book, there's something called an inference toolbox. On the AP test and on my test, it's probably not going to say follow the inference toolbox. So what I have done is I have come up with an acronym for you that will help you to identify all the major components of a confidence interval. So these are basically the 4 steps in the inference toolbox, which is specific to your textbook. So again, they're not going to tell you on the AP test, follow the inference toolbox. But anytime you are asked to construct a confidence interval, you are going to follow the acronym PANIC. P-A-N-I-C. Okay? The P stands for identify the population of interest and the parameter that you are constructing the confidence interval for. A stands for verify assumptions or conditions. So those are the 3 things we talked about in the earlier slide. Random sample, check for normality, and check for independence. Name the test or interval. So that would be 95% confidence interval for a proportion. And then the last thing is IC, interpret your results in the context of the problem. And that's basically the 2 sentences where you interpret the interval and then you interpret the meaning of 95% confidence or 90% confidence. So when I see you next, we will go through an example and we will follow this acronym PANIC. And this way you're covering everything that the graders look for and you are showing your knowledge of what it takes to create a confidence interval and how to interpret it. See you later, ladies.